All right, good afternoon. Uh, Again, we were looking into functions and most recently into operations between functions. And now, for what we have, just looking at the exercises that we have on page 225. Okay, and we have regarding numbers 10 through 26 even. We have for the first portions, okay, we have introduced three functions whereupon we have f of x is equal to negative 2x, g of x is equal to the absolute value of x plus 4, and we have h of x is equal to 1 over x minus 3. Now, up to this point, I have looked at operations between functions in the general format, and what I'm going to be looking into is going to be involving looking into specific format, okay, especially where you have specific values for the input. Now, for what we have in the case of number 10, we're looking at determining what the outcome will be for g minus h of 2. Now, for number 10 and number 12, I'm going to show you a couple of different ways of doing these problems. The first approach will be the general case, and the second approach is going to be the general case. And for the rest of the items for specific inputs, I'm going to be applying the specific case. Now, for g minus h, okay, if I look at this through the framework where we have g minus h of x, here we have a difference of functions where if we look at writing and expanding on out, this is going to translate to g of x minus h of x. And for the variable expressions to which each function is set equal, well, for g of x, I have the absolute value of x plus 4. And then we have minus h of x, where I have the subtraction of 1 over x minus 3. All right, so we've got the absolute value of x plus 4 from g of x, and then subtraction, and then of h of x, which I have at 1 over x minus 3. Now, for the input value at 2, so we have g minus h of 2, and replacing x with 2, so I have g of 2 minus h of 2, and carrying 2 to replace 4, or say x, I have 2 plus 4 in the absolute value, and we have minus 1 over 2 minus 3, and I'll just work down over here. So you have the absolute value of 2 plus 4, so this will be the absolute value of 6. And for 1 over 2 minus 3, have 1 over negative 1. And following through, so the absolute value of 6 is going to be positive 6. Now we've got minus negative 1. And subtracting a negative will be the same as adding the positive of 1. And so for this output, we have 6 plus 1, which will be at 7. Okay, so g minus h of 2 is equal to 7. Now, another approach, again, just applying the specific case. Okay, so just looking at it with the specific case approach. So again, we have g minus h of 2. Again, it still translates out to g of 2 minus h of 2. And what we can do is that instead of arriving at the variable expression, we can go ahead and determine the values of g of 2 and h of 2. So again, so if I were to move to the side and determine just what g of 2 is. Now g of 2, okay, this is going to be the absolute value of 2 plus 4. Absolute value of 2 plus 4 is the absolute value of 6, which is still at 6. And in the case of what we have for h of 2, again, h of x is 1 over x minus 3. And with x at 2, again, we have 1 over 2 minus 3. So we have 1 over negative 1, so we have minus 1. Okay, and so just following through. Okay, so for g of 2 minus h of 2, okay, g of 2 we have at 6 minus, and h of 2, again, we have at negative 1. And we have with the follow through. Okay, so we have 6 minus negative 1, so we have 6 plus 1, which will be at 7. Okay, so two slightly different approaches, and both of them are nonetheless correct. And if I'm looking at just working with one input, maybe two at the most, I would likely prefer to go with just the specific case. But if I know that I'm going to be dealing with a lot of inputs, like not just 2 or 5, but looking at, say, like a dozen different inputs, that might be a case of where it would be an advantage to go ahead and apply the general case and just have that formula stored and put in all different kinds of values for x. But if I'm looking at just one input or two inputs, I think I would go with the specific case. Now, for what we have in the case of taking what we have with the same functions and carrying over to what we have for number 12. And so, again, so we have for this trio, this side. All right, so we still got the same f of x, g of x, and h of x. And this time around, I'm looking at h times g of 4. And it's with this second problem, this will be the last one where I will be looking at the general and the specific cases. For h times g of 4. Okay, again, just for the setup here, if I take the general case, in other words, apply the expressions in x before the number. So you have h times g of x. So this will be h of x times g of x. And h of x, we have 1 over x minus 3. And we have g of x, which we have as the absolute value of x plus 4. And for the product here, we're going to be looking at the absolute value of x plus 4. And then you will have divided by x minus 3. And for the input value of 4. So we have for h times g of 4. So we have h of 4 times g of 4. And here we have plugging in 4 for x. So we have the absolute value of 4 plus 4. All over 4 minus 3. So this will become the absolute value of 8 over 1. And upon simplifying, so absolute value of 8 is 8. 8 divided by 1 is at 8. And again, if I apply the specific case, so again for h times g of 4, so I have h of 4 times g of 4. Okay, so for h of 4, again referencing h of x. So you have 1 over 4 minus 3. And you have 1 over 1, so h of 4 is equal to 1. And in the case of g of 4, I have the absolute value of 4 plus 4. And so we have the absolute value of 8, and that reduces to 8. And so we have in the follow through, so h of 4 we have at 1. Okay, we have 1 times 8. And we have is equal to 8. All right, and again, different route, okay, but still the same value. All right. Now, still with the same functions, we have assigned for f of x, g of x, and h of x. Okay, and if we continue and apply what we have in the case of number 14, and 14, we're now looking at working with the operations, okay, between functions. In this case, we have f plus h of 5. Okay, and from here on out, okay, I'm going to apply the specific case. All right, so we have with f plus h of 5. Okay, so this will become f of 5 plus h of 5. And okay, so looking at what we have for f of 5 and h of 5. Again, so if I arrive at the specific values, so for f of 5, okay, so referencing negative 2 times x, f of 5 is going to be negative 2 times 5, which will be negative 10. And for h of 5, so you have 1 over 5 minus 3. And so you have 1/2. So filling in the specified values, so we're going to have negative 10 plus 1/2. And that is going to be equal to negative 19/2. So we're going to have a negative non-integer in the result. And you can write that as a negative fraction or decimal or mixed number. Any way that you cut it, okay, any variation of negative 19/2, whether it's negative 9.5 or negative 9.5, that will be correct. Now, for what we have in the case of the next even numbered item, and this time we have working with quotient functions. And for what we have in the case of number 16, okay, so this time we have h over f of x. Okay, so we have h of x over f of x. Now we have with the specified input, now we're looking at h over f of 7. So you have h over 7, h of 7 all over f of 7. And okay, so you have with the h and the f values. And so just taking what we have here. So just looking at at the specific values. So just plugging in for what we have for h of 7. Okay, so you have 1 over 7 minus 3. Okay, so that's going to be at 1/4. Now, in the case of f of 7, so you have an f of 7. Okay, so again, your f of x, you have negative 2 times x. So for f of 7, we have negative 2 times 7. So this will be at negative 14. Now we have in the setup, okay, we have h of 7. So we have a fraction with 1/4, and that is in the numerator. Now for f of 7, we have a minus 14. So you got a bit of a complex fraction, not in the sense of like the letter I, not the complex number system, but where you have a fraction where the numerator or denominator, or both, will consist of a fraction. And so way to clean this up, okay, is that, okay, so we got 1/4 at the top, and if I divide by negative 14, I can say that I have 1/4 times the reciprocal of negative 14, so this will be minus 1/14. And for what we have here, we got a positive times a negative is a negative. 1 times 1 is 1. 4 times 4 comes out to 56. So for h over f of 7, okay, this value comes out to minus 156. Okay, now okay, what I did here, okay, because I had 1/4 divided by negative 14, and another way you could have gone about this, say like, say like 1/4 divided by negative 14. I wanted to make this into not a fraction over a number or number over a fraction. What I did, essentially, if I got like 1/4 divided by negative 14, that's the same as 1 over 4 times negative 14, and that's negative 1 over 56. And there's, I don't know if they still teach this stuff, but there used to be like some of these property shares, like if you have something like a over b divided by c, this would condense down to a over, okay, we have the denominator of this ratio, okay, we have a over b times c. So a fraction, yes, yeah. Because if you have, I'll give you an instance. Say if you have something like 3/4 over 7. So if I'm dividing by a number, say like a whole number, it'll be the same as multiplying by its reciprocal. I'll give you a little visual. How about this? Yeah, if you see a whole number, you say, okay, think of like 3/4 divided by 7 over 1. Either way, that would still come out to 3 over 28. But yes, you can write a number, even if it's in the denominator. You can write that as a number and then just flip it, and that will be your result. All right. Now, for what we have in the case of the next item, okay, and still working with our trio of functions, still in f, g, and h. Okay, and this time around we're looking at h over g of -4 okay, and we have with h over g of -4, so again you will have h of -4 divided by g of -4. And if I applied the specific case right away, okay, so you have with, if I go ahead and identify h of -4, h of -4, so I have 1 over -4 minus 3. And so you have like 1 over -7 or -1/7. And for g of -4, so we're going to have the absolute value of -4 plus 4, and the absolute value of 0 is equal to 0. So if I fill in, okay, so you have h of -4, again, so I have -1/7. And dividing by g of -4. And guess what? G of -4 is 0. And right away, if you notice the bottom number is 0. So that means that the outcome for 18 is going to be undefined. Because in a rational expression, the bottom number cannot be equal to 0. And once again, it's undefined because of the denominator. All right. Now, for the next group, okay. Now there are going to be 3 other functions, but I'll tell you what. Let me provide a little bit of a segue, just with just some examples here, where the domain is concerned. And let's say that if you have given, and so you have 2 functions. Say we have given, say we have f of x is equal to, we'll say that we have 1 over x minus 7. And we have that g of x is equal to, and we'll say that we have the square root of x minus 3. Okay, so here to determine the domain, of the sum, the difference, the product, and the quotient function. Okay, and let me just restate. Okay, now for the sum, difference, and product functions, okay, those are going to have the same domain. Okay, all right, and let me mention, okay, so for f of x equal to 1 over x minus 7, okay, now we have a fraction. And for this fraction to be defined, okay, the bottom part cannot be 0. So x minus 7 cannot be 0. So x cannot be equal to 7. All right. Now for g of x equal to the square root of x minus 3. Remember, for what we have the real number system, for an even root of an expression to be defined, that expression cannot be negative. So x minus 3 cannot be negative. It can be greater than or equal to 0. And if that is the case, then what is allowed for x is that x must be greater than or equal to 3. Okay, now for the domain of the sum, difference, and product functions, their domain will be defined by combining the restrictions of f of x and g of x. So we have a bit of a twofold situation here. Okay, so we have for these, okay, to keep f of x defined, x cannot be 7. And for what we have, okay, to keep g of x defined, we also have it that x must be greater than or equal to 3. Okay, now if I have g of x in direct terms now, you can have the square root of 0 if you got your expression in direct terms. Now the square root of 0 is going to be 0. Okay, now for this particular set, just looking at the visual on this one. So for the numbers of concern, okay, so you have 3 as well as 7. Okay, now x cannot be equal to 7. So we have a hole on 7. Now for x greater than or equal to 3, okay, now we have equal to 3 in the inequality statement. So 3 is going to be included. Now everything else that we have for x so far, okay, had to be greater than. Well, guess what? If we proceed to the right, okay, so proceeding to the right, okay, so you have greater than 3, you have like going past 4, 5, 6. Now we have approaching 7, but again, you have this aforementioned restriction that x cannot be 7 because we still have to be able to work with f of x. So 7 is going to be left out. So this part about x being greater than or equal to 3, it's going to have everything including 3 and greater than 3 except for the number 7, since 7 cannot be included. But once we bypass 7, we're going to have resuming the activity and going out to the right. And we have approaching infinity. Okay, so for what we have in this case, now we have combined restrictions. Now we have x is greater than or equal to 3, and had that been the only restriction, I'll have a ray going to the right non-stop toward infinity. But because I have to work with f of x and the x cannot be 7, that ray is not running continuously from 3. So what's going to happen here is that for this same domain that we have for the sum, difference, and product functions, this will be broken up into 2 sections here. And so we have starting from and including 3. So 3 is going to be in the brackets. And we have approaching but not including 7. So 7 is going to be in the parenthesis. And bypassing 7 and resuming the activity. And so we have, for the second half, okay, had those values of x greater than 7. So that would be the domain for the sum, difference, and product functions. Okay, so again, first 3 operations, you have the same domain, And here, okay, we have, again, going from and including 3, approaching but not including 7. And then we have for the rest, you have those values of x greater than 7. All right. Now, and again, f over g of x in terms of the domain, okay, this can potentially be the odd man out. Okay, now for f over g of x, now if we're looking at the function itself, and it's like we had to work this one out to see if there's going to be any added restrictions to be included, along with x cannot be 7, or x cannot be greater than, or x can be greater than or equal to 3. So we have for f over g of x, so we have f of x over g of x. Now for f of x, again we have 1 over x minus 7. Okay, so for f of x, we have 1 over x minus 7. And we have for g of x, now g of x is going to be the square root of x minus 3. And guess what? We have for the conditions here. Now, we still have f of x. F of x must be defined. Okay, here we have f of x as the fraction 1 over x minus 7. So we still have the x cannot be 7. Now, if you notice, we have in the ratio, okay, you have initially the square root of x minus 3. You have g of x, you have the square root of x minus 3. And for what we have here, see if we simplify, so you have 1 over x minus 7. And you have times 1 over the square root of x minus 3. So for this outcome, I have 1 over the quantity of x minus 7 times the square root of x minus 3. Now, in this deal, again, to keep f of x defined, okay, again, we have x minus 7 cannot be 0, so x cannot be 7. Now for the g of x part, now g of x is situated in the denominator. And so we have what's going to be a twofold restriction. Okay, and again, because we have a square root, okay, we have the x minus 3 cannot be negative. And also because we have x minus 3, its square root in the denominator. We had that x minus 3 cannot be 0. So running the filters, it's going to follow that x minus 3 must be positive. So that means that x minus 3 has to be greater than 0. So we will have that x is greater than 3. Okay, and so for the restrictions, okay, for what we have in the quotient function, it's going to follow that along with x not equal to 7 we're going to have the other remaining values of x to be such that x is not greater than or equal to 3, but just greater than 3. And so for the quotient function, okay, so again we have our points or values of concern at 3 and 7 once again. And so this time we have on 3 with x is greater than 3. We have a hole, not a solid point, but a hole on 3. And again we have a hole on 7. Again, so for x is greater than 3, again I'm going to start out with activity. So again, just proceeding to the right of the hole at 3, and then again we have 7 is excluded, and we have continuing with array going to the right, and once again proceeding out toward infinity. And you almost had the exact same domain, but for the domain of the quotient function. What's going to happen here is that with 3 excluded, we're going to have a parenthesis around 3. So we have approaching but not including 7. And for the rest, okay, have those values of x which will be greater than 7. All right. So again, we have almost the exact same domain this time around, but again, the quotient function is going to have a slightly different domain, and that is because with g of x in the denominator, I had to keep x minus 3 positive only, okay, because this time around with g of x in the denominator, it had the added burden of not only not being negative, but also not being 0. And thus, we had the exclusion of 3. All right. Now, for what we have in the case of the even numbers, this time we're shifting over from functions in f, g, and h of x to what we have with, I think it's r, q, and p of x. Let me double check these numbers here, and we have R, P, and Q. Okay. Okay, so you have, starting out, okay, so you have R of x is equal to negative 3x. And P of x we have is equal to x squared plus 3x. And for Q of x, we have equal to the square root of 1 minus x. And so just looking at the functions, and since we're going to be attaining not only the concerned operations for these exercises coming up, but I'm also looking for the domain. Now with R of x and P of x, you don't have a fraction or an even root radical, so we don't have any restrictions placed upon R of x or P of x. Now on the other hand, for Q of x, I have an even root radical. Again, so whatever we have for x for Q of x, 1 minus x cannot be negative. Okay, so you have 1 minus x is greater than or equal to 0. And if I get the x term by itself upon moving 1, we have by subtracting. Okay, so we're going to have that negative x is greater than or equal to -1. And again, if I change the signs, say if I multiply or divide by -1, the direction of the inequality changes. And so here we're going to have the x is less than or equal to 1. All right. So we have with our restrictions, again, r of x alone has no restrictions, p of x has no restrictions, and for q of x, the square root of 1 minus x in direct terms is going to be defined as long as we have the x is less than or equal to 1. Okay, so just again, just laying the foundation. Okay, so again, r of x and p of x have no restrictions. Q of x, okay, we have restricted, okay, for x, the limitation that x be less than or equal to 1. And now, for what we have in the case of number 20, okay, so we're starting out with p minus r of x. Okay, and if you notice, okay, now again with the sum, difference, and product functions, I can go ahead and determine the domain on the basis of combining the restrictions of those immediate functions involved. So I'm involving the functions p of x and r of x, neither of which have restrictions. And guess what? P minus r of x, as long as you're looking at the sum, difference, or product of these functions, the domain will be on the basis of combining the restrictions. And without knowing what p minus r of x is, I can still arrive at the domain. And with no restrictions at all, the domain is going to be the set of all real numbers. So I can plug in anything for x in the difference and still come out to a real value. So for p minus r of x, for what this is going to be specifically, okay, so we have p of x minus r of x. And so we have with, I'll just work down, p of x I have as x squared plus 3x. And minus r of x I have the subtraction of negative 3x. So I have x squared plus 3x, and the subtraction of negative 3x, we have another plus 3x. And so for the result here, this is going to be x squared plus 6x. So, and again, r of x had no restrictions, p of x had no restrictions. So there are no restrictions from either of these functions to apply to the sum, difference, or product functions among the variations of p and r. And again, so the domain we have as all real numbers. Now, for what we have in the case of number 22, okay, so this is where we can look at combining restrictions. And for what we have in number 22, okay, this time we're looking at r times q of x. Okay, so for r times q of x, okay, so this is one of our 3 operations where we can just combine the restrictions and go ahead and get the domain. Okay, so we have r has no restrictions, and Q has the restriction x is less than or equal to 1. So again, you have R with no restrictions. However, Q has the restriction that x is less than or equal to 1. So for the product, combining the restrictions, we have only one restriction, and that's going to be that x is less than or equal to 1. Okay, so for x is less than or equal to 1, just looking at what we have from a visual standpoint. So the number of concern we have at 1. And for x is less than or equal to 1, okay, so you have a solid point on 1. And then we have a ray to go continuously out to the left. Okay, we have approaching negative infinity. Okay, so for the domain, of r times q of x, so again we have proceeding from negative infinity, and we have approaching and including 1, and the 1 is going to be in the bracket. So again, for this portion, okay, that is going to be the domain. Now for the results in multiplying out r and q of x, and there's really nothing much to do here because we got r of x as a monomial term and q of x as a radical term. So you have r of x times q of x, and the product we have negative 3 times negative 3x times the square root of 1 minus x. And so, yeah, so those are going to be locked in together, okay, because you can't just distribute negative 3x over the square root of 1 minus x. So that would be the resulting product function expressed fully, whereupon we have negative 3x times the square root of 1 minus x. Now for the next items, okay, we have dealing with quotients. And for what we have in the case of number 24, let's see, that one has is q over r of x. Okay. Okay, so for q over r of x, remember, I'm going to have to work this out to fully determine all the restrictions. Okay, and I'm just going to mention, okay, now we have, again, right now r of x and q of x are still involved. R of x has no restrictions. Q of x, we have x is less than or equal to 1. Okay, and I'm just going to kind of, since I'm dealing with the quotient function, I can't just combine restrictions necessarily to get the domain of the quotient function. Okay, so I'm just going to state this only restriction so far. For the only restriction so far, okay, this will come from q of x, whereupon we have the x is less than or equal to 1. But there might be more to the story in terms of what is restricted, since I'm not dealing with the sum, difference, or product function, but the quotient. So finding out what we're going to have now, okay, we have for q over r of x. Okay, so we have q of x over r of x. Okay, so q of x, we have the square root of 1 minus x. And r of x, we have negative 3x. Now for the ratio. Okay, now this one is already going to be in simplest form. But now in terms of what we have, okay, for the domain. Okay, now if you notice you have the square root of 1 minus x, okay, that is at the top. So you can have the 0 numerator. That part will be defined for x is less than or equal to 1. Now, r of x alone has no restrictions, okay, but when you're dividing by r of x, you have a separate restriction that is going to be created. And because r of x is situated at the bottom, okay, we cannot have the bottom part of a fraction to be 0. So we have the x cannot be 0. Okay. And so for q over r of x, okay, it's going to turn out that, okay, when we started out, okay, and in terms of the restriction, now we have from the square root of 1 minus x, again, we had the restriction that x is less than or equal to 1. And again, we have with negative 3x, which was assigned, okay, from r of x. Okay, again, the denominator cannot be 0 in value. So we have with the other restriction, okay, we have that x cannot be equal to 0. Now for the domain of the quotient, and so we have with the numbers focused upon, okay, so we have 0 and 1. Okay, so x cannot be 0, so we're going to have a whole on 0. Now for x is less than or equal to 1, for x is less than or equal to 1. Okay, so I have the equal to part here, so I'm going to have a solid point on 1. And if I go with less than, okay, now I would otherwise be going continuously to the left, but again, x cannot be 0. But once I get past the exclusion of 0, I can then proceed continuously to the left. And have a ray that is going to go out to the left. So, again, we have approaching negative infinity. So for the domain of the quotient function, okay, so you have going from negative infinity, approaching but not including 0. So you have a parenthesis, and then we have in the follow through. So you have going past 0, so you have another parenthesis, then you have 0, and we have approaching and including the value of 1. And the 1 is going to be in the bracket. And okay, now for 26, now we're flipping the fraction, so to speak. And this time we have r over q of x. Okay, and for what we have here, so we got a quotient function. Now, so far, I'm just going to mention it because, again, we're dealing with the quotient function. So yeah, the only restriction so far is going to stem once again from q of x. So you have that x is less than or equal to 1. Okay, but again, there could be more to the story since we're dealing with a quotient function. And for R over Q of X, so you have R of X over Q of X. And so this will be negative 3x all over the square root of 1 minus x. Okay. Now in terms of where the domain is concerned, okay, now Q of x, you have square root of 1 minus x. And again, because for the square root portion, from which, again, this restriction originated, again, we said that x minus 1, make that x, not x minus 1, but 1 minus x cannot be negative. But also, okay, now Q of x, x is less than or equal to 1. That would be its only restriction if Q of x were given in direct fashion. But since Q of x is in the denominator, 1 minus x cannot be 0 either. And with the combined limitations, okay, that means that 1 minus x must be positive. So that means this time, okay, so we have 1 minus x must be greater than 0. And for isolating the x term, so we have taking 1 away from both sides. So we're going to have that negative x is greater than negative 1. And again, if I change the signs, whether it's through multiplying or dividing by a negative, once again, do not forget to change the direction. Okay, and so we're going to have that x is less than 1. Okay. So for R over Q of x, okay, notice I had said only restriction so far, and the reason I said so far is that we're dealing with the quotient function. So there could have been another restriction created, and guess what? That added restriction disallowed x from being equal to 1. So for R over Q of x, the restriction is going to be not x is less than or equal to 1, but that x is less than 1. So we have with the number 1, okay, and with x being less than 1, so we're going to have a whole on 1. And from this, okay, we're going to have a ray that will go continuously to the left. We have approaching negative infinity. So for the domain of this quotient function, so for the domain of R over Q of x, okay, so we have parentheses, okay, so you have going from negative infinity approaching, but not including the value of 1. So this will be the outcome for this particular rational function's domain. All right. Now, again, with the sum difference in product function domains, again, it boils down to just combining the restrictions of the immediate functions involved. However, with the quotient functions, again, in terms of how the cookie crumbles whenever you're simplifying the ratio and looking at what is in the denominator, it is possible that added restrictions will be applied outside of what we have for the individual functions domains involved. And that had to be the case with these last two items. Now, for what we have in the case of our other types of functions, and this will be what we have with the composition of functions. And upon first glance, okay, this might appear to be something that might strike you as multiplication, but it's going to be an entirely different operation. And in the case of what we have regarding composition of functions, and for our functions f of x and g of x. Okay, so for compositions between the functions, okay, we have, first of all, some might just refer to this as fog x, because it's like the letter O separating the symbols. Okay, but this circle here is not in reference to multiplication. Now, if I had a closed circle, this is like dot multiplication, but here the open circle signals that we're looking at a composition of functions. So for this notation, this piece here is read f composed with g of x. And for what we have operationally, okay, so we have with f composed with g of x. If I were to write this in any other notation, this would be f of g of x, where the g of x part, okay, that is going to be the input. And in the case of f, okay, f is going to be the output. And you can also reverse the order of the functions in the composition statement. So you have like going from fog x to goth x. Okay, this statement is going to be read, okay, g composed with f of x. And so for this layout, okay, so you have for g composed with f of x, okay, that's equal to g of f of x. So there's a bit of a turning of the tables in terms of what is going to be the input and what is going to be the output. So now we have that which represents f of x, okay, that is the input. And of course, the operational follow-through is going to be with what we have in accordance with g, okay, where the g part is going to be the output. And let me give you just a case of what we have for specified functions. And let's say that if we have So if we're looking at both compositions, f composed with g of x and g composed with f of x, and we have given, and we'll start out with a couple of linear functions. Okay, and we'll say that we have f of x is equal to x plus 2, and that g of x, okay, is equal to 2x plus 3. All right, so for the first composition, okay, so we have for f composed with g of x, so we're looking at f of g of x. Okay, all right. And if you notice, okay, now f is going to be the output function, and let me just kind of restate here. So f of the input is going to be equal to the input plus 2. Okay, now here in the compositional function, okay, we have not x but g of x is in the parentheses. So for f of g of x, okay, now again, f of the input is equal to the input, which we have at g of x plus 2. Now, and what's g of x? Well, g of x is going to be at 2x plus 3, so we can just fill in the variable expression. And we have been following through, so you have 2x plus 3 plus 2, and that outcome is going to end up at 2x plus 5. And if I take the reverse order, and we have with g composed with f of x. So now I have g of f of x. And just for sort of the backdrop here, so the output function, okay, we have at g. And again, just referencing what is given. So g of the input is equal to 2 times the input followed by the addition of 3. Okay, now the input here in the composition, okay, we're going to have 2 times f of x followed by the addition of 3. And again, just specifying what f of x is. Okay, so f of x, we have an x plus 2. So 2 times f of x is going to be 2 times all of x plus 2, followed by the addition of 3. And we have with distributing. Okay, so you have 2x plus 4, followed by the addition of 3. And so we have for this output, okay, this will come out to 2x plus 7. And another case here that we have concerning compositions. And we'll say that we have, let's go with some quadratics here. We'll say we have f of x is equal to x squared minus 3. And that g of x is going to be equal to 2x plus 1. And for the composition, okay, where we have f composed with g of x, Okay, so you have f of g of x. Okay, so after sort of clustering together, okay, now remember the output function is symbolized by f. Okay, so here we have working along the lines of function f. Now again, f of x equals x squared minus 3. Okay, this is signaling that f of the input is equal to the square of the input minus 3. Now with the input at g of x, so again, f the input, square the input minus 3. So now we're going to have the square of g of x minus 3. Now for g of x, now g of x is the binomial, 2x plus 1. So moving on down, okay, so you have the square of 2x plus 1 followed by the subtraction of 3. And squaring out 2x plus 1, so we have 4x squared. And then we have 2x plus 2x, which will make 4x, and then we have plus 1. And we have followed by the subtraction of 3. And so we're going to have, for this end result here, we have 4x squared plus 4x minus 2. And for the reverse order, and for g composed with f of x. Okay, so you have g of f of x. And again, what do we do with f of x? Well, we treat it as if it were x in g of x. Okay, so we got in this one. Okay, so you have g of x is equal to 2x plus 1. So whatever the input is, you take twice that and add 1. So for g of f of x, so you're now going to have 2 times f of x followed by the addition of 1. And again, f of x we have at x squared minus 3. We've got plus 1, and in the follow through. Okay, so you have 2x squared. 2 over negative 3 becomes negative 6, and we have plus 1. And so for the result here, okay, this will come out to 2x squared minus 5. And just want to mention something regarding the composition of functions. And this will be for what we have concerning its domain. And I'll just kind of give a layout for the domain. Okay, so you have for the domain of a composition, will be formed by combining the restrictions again, combining the restrictions of the input function and of the composition itself. Okay, and we'll say that we have in this particular layout. Okay, I'm just going to give you just kind of something that's not going to be all real numbers. let's say that if you're looking at and we'll say that we have let's say we have 1 over x minus 2 for f of x and g of x, we'll say is equal to x minus 3. So for f composed with g of x, so you're looking at f of g of x again in accordance with f of x, so f of the input is equal to 1 over the input minus 2. And guess what? So we have in the follow through, so you have 1 over g of x minus 2. And guess what? For g of x, okay, we have 1 over x minus 3 minus 2. And if I combine the terms together, now we're going to have for the final composition, okay, that's going to be 1 over x minus 5 okay. Now again, input the input function have g of x equal to x minus 3. So there is no restriction for the input. But once I apply it to the setup in the composition, well, guess what? For the output, the composition itself, the output x minus 5 cannot be 0, so x cannot be equal to 5. So between combining the restrictions of the input and the output, the only restriction is going to come from the output where the x cannot be equal to 5. So we have for the domain of this composition, you're looking at all real numbers except for 5 and just for the interval notation. So we have those values of x less than 5, first portion, and then the other subinterval. And we'll have those values of x which will be greater than 5. And that will be the result that we have once again for the domain of f composed with g of x.